Good evening, everyone. Welcome to the week 4 live interaction session for this course, Technologies for Clean and Renewable Energy Production. So let's just wait for a few minutes for others to join before we begin our session for today. So I think we can start our session for today. So let me just share my screen. I hope my presentation is visible and I'm audible. So let's start our session. So, good evening, everyone. Welcome to week 4 live interaction session for the course Technologies for Clean and Renewable Energy Production. This course is offered by Professor Prasenjit Mondal sir from the Department of Chemical Engineering, IIT Roorkee, under the NPTEL SWAYAM program. Myself, Pratyumnan, a PhD research scholar from the Department of Chemical Engineering, IIT Guwahati. So, I conduct live interaction session for this course for the July-November 2026 semester. So this is our fourth live interaction session, and with this live interaction session, we almost complete 50% of the course. So far we have discussed about the technologies so initially we had a brief overview on the reason why we are focusing more on energy production and how energy production becomes a currency for the country's development. And then we discussed on what are the different kinds of energy that a particular country uses to meet its demand. We discussed why the demand is increasing and what are the kind of energy that a country or that is commonly being utilized in the recent days for meeting these energy demands. So then we discussed about the crude oil, coal and coal gasification, and in the last session we also discussed about the crude oil and the refining process. So in today's live interaction session, we will purely focus on impurities removal and the residue upgradation. So, by what I mean by the impurities removal is, in case of this crude distillation or any kind of cracking or any kind of refinery process that you do in order to obtain the different kinds of products. Like for example, in the last session we discussed about the um, fractional distillation, wherein this petroleum products, when it gets when it undergoes distillation, it also produces multiple other side products which have their own application. So during these conditions, what usually happens is the byproduct that you are going to get is not going to be actually very pure in nature. So they are going to be contaminated with the impurities. So these impurities actually degrade the quality of the oil or quality of the product in general. So if you remember in the last live interaction session also, we basically discussed about something like how sulfur actually affects the quality of the petroleum products. I said higher the sulfur content, cheaper it will be of a low quality fuel oil, and that is makes it more cheaper in rate. Whereas making it more pure or improving the quality of the oil, you basically try to remove the sulfur from the oil, and that actually improves the quality, and that translates to higher price of the fuel. So these impurities need to be removed so that the efficiency of the products that you obtain from them is good. Like for example, in case if it's a oil, the purity of the oil becomes good if you remove the impurities, so that they can provide more efficiency, more energy, because these impurities will sit within the oil and they will start consuming energy for itself, and they may remain, and they may be inert also, so they may eat up the or decrease the efficiency of the fuel. So due to that process, the impurities needs to be removed from the product. And the other reason apart from the quality of the product is, when you take this fuel oil or when you take any kind of petroleum products, you may also be using them for further processing, some sort of cracking or some kind of a polymerization. So if you are going to not purify them, and then if you are going to actually use them for the process, then they may contaminate that product as well. And in case if some catalyst is involved, as all of you may know, catalyst is quite expensive in nature. So you need to put more amount of money even for a small amount of catalyst. So because of that, the catalyst poisoning may also happen because of this impurity. So they may not be effective in the reactions what they are supposed to, in reactions where they are supposed to work. So that actually decreases the efficiency of the catalyst. And since this catalyst is expensive, majority of our focus is also in a reaction process is also on the recovery of the catalyst. How can we recover the catalyst? So that better term to use other than the recovery is to regenerate the catalyst. How can you use the catalyst that you used once, so that it can undergo some sort of a very simpler downstream processing, and from there you can reuse the catalyst again. So impurities also affect the quality of the catalyst that is involved in the process, or that is involved in further processing of the distillate product. So that is major focus on why impurities needs to be removed. And the impurities as such, if you see, they will be the main impurities in these case, so in these kind of petroleum products are nothing but it could be sulfur, nitrogen, oxygen, and some sort of dissolved metals, organic salts, soluble and insoluble. So these are the kind of impurities that is going to affect the uh, products that you are obtaining from a particular process. So these impurities needs to be removed. So our main focus towards this in live interaction session will be to understand, or probably for the week 4 course is to understand how to remove these impurities. So for so when we talk about multiple kind of impurities that are present like sulfur, nitrogen, oxygen and dissolved metal, the first thing that we will discuss now is the removal of sulfur from the distillate products. So that process of removal of sulfur is called as sweetening. Oh. So removal of sulfur compounds. That process is called sweetening. And the sweetening is of four different sorry. Oh. And the sweetening is of four different kind of what do you say? There are four different process. Anyone who is aware of that four different process? The four different process for sweetening. Anyone? Four different process for sweetening. Or basically saying four different process of sulfur impurities removal. Okay. So if you happen to go through the course contents, you will be able to see these four process that is mentioned in this slide. So one is caustic wash, another one is doctor treatment, or you can also say or you can also call it as doctor sweetening. Then copper sweetening. Another one is called Marox process. So we will discuss all these four processes to in brief. So in case of caustic wash, what you do is you basically try to extract the sulfur compounds using a base. So that will be either sodium hydroxide NaOH or potassium hydroxide KOH. So in case of caustic wash, you use sodium hydroxide or potassium hydroxide, and then you make them react with the petroleum fractions. So usually the sodium or the potassium hydroxide will not be like in the form of, they are usually available in the laboratory in the form of pellets. We make solutions out of them. So that particular you can say water solution of NaOH or KOH is called lye, LYE. So they have a specific term. Water solution of sodium hydroxide or potassium hydroxide is called lye, Lye. So this lye basically reacts with your petroleum fractions to basically remove the sulfur from the petroleum fraction, and that is the it's basically used for the extraction of sulfur from the petroleum fractions. So this is one type of sweetening process called caustic wash or caustic sweetening as well. So here typically the reaction goes like this. So you have the sulfur product. So this form of writing RSH, they are also called as mercaptans. Plus sodium hydroxide. I am taking the example of sodium hydroxide. Gives NaSr plus H2O, water. So this NaSr is the product that you obtain from this caustic wash, So basically in this process, so this process is usually carried out at high temperature and then with a high concentration of lye. But here we need to basically keep this in mind that the concentration of this lye, when I say high, it varies between 1:1 to 1:10. Because if you happen to exceed this particular concentration of the lye, then at high temperature and at such high concentration of the sodium hydroxide, there can be chances of corrosion and a loss in stability of the petroleum products, and some sort of color formation will start happening. So that is typically becomes the disadvantages of this process. So the high temperature and high concentration that is used in this process is typically basically causes for the stability loss. So both of them need to be optimized so that you can extract the sulfur from the petroleum products. And then the spent lye can also be used for removing the other minerals and organic acids from the petroleum products, so they can be typically regenerated. So in this case, in case of, so in all these different kind of sweetening process, it's basically their main focus is one thing, to remove sulfur from the petroleum fractions. What kind of reagents you use in order to do these three processes only makes them different from each other. So that also I'll mention it here. Reagents for the reaction is different. So it's just that the reagent that you use for this reaction purpose or for the sweetening purpose is going to be different. However, in all these four cases, the main goal is the same, removal of sulfur from the petroleum fractions. So in case of caustic wash, you use sodium hydroxide or potassium hydroxide, which is called as lye. That lye basically reacts with your sulfur compounds. Here typical example we take is the mercaptan. So this mercaptan is going to react with this concentrated sodium hydroxide or potassium hydroxide, forming some sort of sodium based sulfur compounds plus water. So this process is typically carried out at high concentration of lye and temperature. However, one of the major problems that arises is, since it is happening at high temperature and high concentration, there are chances of stability loss and some sort of color formation in the petroleum products. So next process that we go is basically called as a doctor treatment or doctor sweetening. Doctor sweetening. So in case of doctor sweetening process, you are actually going to, the reagent that we are going to use is called as, is nothing but it's, I'll write the chemical formula, Na2PbO2, which is nothing but it is called sodium plumbite. And we are also going to use sulfur. So we are going to use these two compounds to basically extract the sulfur from the petroleum fraction. So again the reaction goes same. So here we take mercaptan as one of the major sulfur based compound in the petroleum fraction, and we are going to make that react with Na2PbO2, which will give PbSr2 plus NaOH, and then this PbSr2 can actually react with the sulfur, resulting in the formation of plus PbS. And there are also chances that this PbSr2 may also react with the oxygen. So if in case if it is going to react with oxygen, it's going to have a problem. So what it will form is, so in case if this PbSr2 whatever is formed in the product, if they are actually going to react with the oxygen, then what typically can happen is it can actually lead to failure in the water tolerance test. So this PbO formation can lead to failure in water tolerance test. Now similarly, just like how the oxygen will lead to certain issues or certain problems or limitation, like that the concentration of the sulfur is also very important. If in case if the concentration of the sulfur is going to increase, then what happens is this RSXR, that is the polysulfide compounds, that concentration will increase, and that will cause failure in the copper foil corrosion test. Whereas if you are going to use less sulfur, then what happens is majority of them is going to remain as oxygen, and PbO is going to form, which will basically cause failure in the water tolerance test. So my question over here, which I would like you to answer is, what is this water tolerance test is and a copper foil corrosion test is like? What do they mean? What do you mean by copper foil corrosion test failure and water tolerance test failure? Anyone? What is meant by, what do they actually, what is this procedure water tolerance test is? What is the procedure for water tolerance test? So kindly find out what is this difference between this two tests, or what are these two tests are for, and what is their procedure. Because when we say that excessive formation of something is actually going to lead to a failure, or it's going to actually lead to some sort of disadvantage or limitation, then we are supposed to know what that limitation is, and why is it of significance for us to read or learn about it. So I think it would be better for the learners to actually go and look at this two different types of tests for this doctor sweetening process. Then comes copper sweetening. So as the word suggests, you are going to use some sort of copper compounds for the extraction of sulfur from the petroleum fractions. Basically here we are going to use copper chloride, CuCl2 or CuCl. So in case of copper, use copper chloride. So what typically happens is mercaptan is present, that is actually going to react with your CuCl2, and it's going to form CuSr, basically copper sulfur compounds, plus HCl plus RSSR. Again, here also same thing. The formation, there are chances of for formation of, so this CuSr may react with the copper chloride itself, leading to the formation of CuCl, that is cuprous chloride plus RSSR, and this CuSr also has a chance to react with the oxygen, leading to formation of CuO plus RSSR. The major problem is that this CuO, similar to PbO, can basically cause failure in this water tolerance test. So that again becomes a limitation in case of copper sweetening test also. So major goal is to extract the sulfur compounds. Again, each and every method has its own limitations and advantages, so we are supposed to know about each of them. Next comes is the Marox process. So Marox process is, it's basically used for, first thing what it does is it's used for the extraction of low molecular weight mercaptans, mercaptans RSH from LPG with alkali and its oxidation to disulfides. It can actually do two things. One thing is extraction of low molecular weight mercaptans from LPG with alkali and its oxidation to disulfide. And another one is conversion of high molecular weight mercaptans to disulfides. So these two Marox process, so these two process are possible in case of this Marox process for sweetening. So the typical reaction is something similar to what you saw in case of caustic wash. So your RSH, that is your mercaptan, is going to react with the sodium hydroxide, leading to the formation of NaSr plus H2O. This NaSr undergoes subsequent oxidation leading to NaOH plus RSSR, or this RSH, that is the mercaptan itself, can undergo oxidation. There is also this possibility where without much reaction to sodium hydroxide, some of the mercaptans may react with oxygen, leading to the formation of RSSR plus H2. So typically in this cases of the oxidation process, here the O2, the amount of oxygen that we are going to send in is going to be in the range of 110 to 200 percentage of its stoichiometric quantity. So whatever the amount of oxygen that is actually required for this process, you are going to send in the injection amount, the amount of air that you are going to send in is going to be 110 to 200 percentage of its stoichiometric amount. So because of that, because of such a high rate of oxygen, what actually happens is this oxygen O2 can itself react with RSH to form for the extraction process. So that itself can cause sweetening. The dissolved oxygen or the oxygen itself can cause sweetening process to happen. That is one advantage. And other advantages of using high concentration of air is it helps in using settling of the catalyst. And another advantage is that you cannot say that is an advantage, but since high rate of oxygen you are going to send in, it can also cause some sort of corrosion within the system. So typically all this process usually happens in case of an oxidizer. So in case of the Marox process, if you happen to see the process flow diagram in your class, in the course content, you can actually see is first you have a caustic pre-wash. After that you have multiple other systems, and then you actually go for a oxidizer. So in this oxidizer you are going to inject, as I said, more quantity of oxygen. So that is actually going to react with your NASR, and that can actually cause the sweetening of the can actually accelerate the sweetening process as such. Now this is about removal of sulfur. So in case of sulfur removal, we have four process: copper sweetening, Marox process, then you have doctor sweetening and caustic wash or caustic sweetening. Apart from this sulfur compound removal, there we are also supposed to discuss about removal of metals. So when you go for removal of metals, you have two different processes. One is a physical method and another one is a chemical method. In case of physical method, you actually have that method is called desalting. And in case of chemical method, you have two process. That is a thermal process, which is nothing but it's whisk breaking and cooking. And another one is the pure chemical treatment. Sorry. So this is a physical method for metal removal. From the petroleum fractions, that is important. So what is this Desalting processes. Anyone? Any small guesses? You may have heard about this process in case if you have happened to work with petroleum. I mean, if you have happened to take courses on petroleum or work in a petroleum industry, then this process you may have heard about them. Anyone? It's basically a physical method. It works on the principle of differences in densities. Again, each and every process is discussed in detail in the course. What I'm doing is I'm just giving a very quick overview on each of them because we do not have time to discuss about each and every process in detail along with their process flow diagram. So this may not be sufficient for you to have a complete knowledge on each of this process. So I request all of you to go through the course content thoroughly so that you can learn about each of these methods in detail. Because when you come, the major reason why I say this is because when we go for these kind of process and process flow diagrams, the temperature, pressure, and kind of their operating conditions, what kind of reactors are used, how the process is happening, their advantages and disadvantages, what kind of reactors are used, all these details becomes important when we discuss about each of this process because a small change or you can say because that's how the process flow diagram is because a small change can actually create the process inefficient, inactive, and a small change in the pressure difference or the temperature can actually make the process less efficient. So each of this process you have specific conditions that needs to be maintained and several optimization levels has to be properly executed, and then you also have catalyst. So each of these components becomes a study of its own. So that is the reason I am emphasizing this time and again in this live interaction session is to basically go through the course content so that you can have a you can have a detailed overview on all these process that is involved in this subject or in this course. So it's a physical method for removal of metals from the petroleum products. So what this process is nothing but the higher molecular weight oils are separated from the heavier asphaltenes by mixing them with the low BP solvent. Low BP in the sense low boiling point, and such as so propane, butane, etc. So nothing here you in order to separate the higher molecular weight oil from the heavier asphaltenes, you are going to basically mix these oils with low boiling point solvent. So once you do that, that separation typically happens because of the differences in the density of both the components. Next comes the thermal treatment, that is your vis breaking and poking. And then comes the chemical treatment called demetallization. So demetallization process is very simple to actually tell it in the form of a, it is very easy to explain it in words. So wherever there is metal in the organic chain, you're basically going to remove that metal from that organic chain with the minimal conversion of petroleum products. Like you're not going to convert the petroleum product from one form to another. You're just going to remove the metal from the organic chain. And for that, you basically go for some sort of demetallization reactions. In case of thermal treatment, you have two different processes. One is coking and another one is called vis breaking. So these two methods we will be discussing soon. So I'll just write for demetallization. This is the process of demetallization. The thermal treatment process, that vis breaking and coking, we will come when we talk about the residual oil concept. So till here we have this impurities removal concept. Any questions? Again, you need to remember a lot of things. So kindly look at the course content, or if you have any doubts, you are welcome to let me know now. Anyone, any queries or questions? So how do you define this residual oil? In case of petroleum fractions, when you do this petroleum treatment, you basically obtain this residual oil. So what is the exact, how do you exactly describe this residual oil? How do you define a residual oil? Anyone? Okay. So residual oil is nothing but it's a colloidal system. Colloidal system. So in case of colloidal system, whenever you describe some particular solution as a colloidal solution, so you will have actually two compounds. One is your dispersed phase and another one is your dispersed medium. So in case of the dispersed phase, it's basically the asphaltenes and resins. And in case of your dispersed medium, it is basically maltings. Maltings are nothing but oil. So a combination of asphaltenes and resins and this oil together, this colloidal system is typically defined as residual oil. And this residual oil, what it actually happens is, if you heat them, if you do some sort of thermal cracking, that is take it to high temperatures, then this oil phase, that is your dispersed medium or the continuous phase, will crack, and then this asphaltenes will basically get released, and this will lead to some sort of a colloidal equilibrium will actually get affected. So we do some sort of a residual oil upgradation. So there are totally three different processes. One is the extraction based approach. Another one is thermal approach. Next one is hydroprocessing approach. So anyone knows what we do in extraction based approach? Yes, anyone? So in case of the extraction based approach, first the method that we are going to follow is solvent desalting. Solvent desalting. Then in case of thermal approach, we actually go for something like cracking and gasification. And in case of hydro processing approach, uh, we actually go for hydro cracking. So as I said, this solvent desalting is same as the desalting process that we actually discussed. Over there, we typically use low boiling point solvent, and then basically we are going to mix it with this higher molecular weight oils, and then we try to separate them from the heavier asphaltenes. So that approach is actually going to remain the same. The commercial solvent that we use in this case is propane, butane, and pentane. Heavier solvents that we are that I mean so just let me write it here. Solvents use is going to be of two types. One is lighter solvents, wherein you will have your propane and isobutane, and the next one is using heavier solvents such as butane and pentane. Basically, the molecular weight actually gets increased in case of heavier solvent because of the increase in the carbon chain length. That's all. And the next approach is cracking and gasification. So here we will go for a concept called wisp breaking, and apart from wisp breaking, we will also have another concept called delayed coking. Wisp breaking is nothing but it's called viscosity breaking, wherein higher molecular weight compounds are broken down into lower molecular weight compounds that has low viscosity and low pour point. So last week also in the concept when we were discussing about this properties of the crude oil, we discussed about cloud point and pour point, and I asked what is pour point. So from did anybody who attended the last live interaction session very able to get the exact definition for pour point and cloud point? Anyone? What is pour point? Just in case if you did not happen to attend the last live interaction session or you were unable to get the definition, then kindly look into this. What is pour point? So wisp breaking is nothing but it's called viscosity breaking, where high molecular weight compounds are converted to low molecular weight compounds which has low viscosity and lower pour point. And depending upon the reactors in which you carry out this viscosity breaking or wisp breaking, you have two different processes. One is called soaker wisp breaking, and another one is called coil wisp breaking. So in case of So only the difference that comes in both these types of processes. So wait, let me just, depending on the type of reactor, you have two different process. One is soaker visc breaking and another one is coil visc breaking. Both these processes typically differ in their residence time. So soaker visc breaking process has a longer residence time compared to the coil visc breaking. So when I say longer visc breaking time, it's usually in the order of 1200 to 1800 seconds. Whereas this coil visc breaking has shorter residence time from about 100 to 300 seconds only. So basically, this soaker visc breaking is a two major conversion processes involved. One is a minor conversion with a shorter period of time, and another one is a major conversion with a longer period of time. So this is about visc breaking, and then we have another something, another concept so called as delayed cooking. So delayed cooking is nothing but it's a thermal cracking process wherein you actually try to the upgrade the petroleum residues by converting them into liquids and gases. So and coke is actually left behind. And then here itself there are basically two types of conversion mechanism. One is primary and another one is secondary. So in case of the primary conversion, you basically break large molecules into small molecules, and in case of secondary, you basically take this active products of large molecules and then you try to crack them to form some other compounds or polymerize them to other products. So basically in all this process, what we are trying to do is whatever the residue that we are going to obtain, we are actually trying to upgrade them so that it can be useful. It can be made useful for some application. So that's how if you see here, we actually were going for we went for this three different process of solvent desalting, hydroprocessing or hydrocracking and thermal approaches. Hydrocracking is nothing but, or hydroprocessing approach is nothing but over there you try to add hydrogen to the system and then remove the other component. So you basically add hydrogen to the petroleum fraction and make it as a more simpler compound. So that is the process of hydroprocessing as such what it means. So then we come for a process called visc breaking, where it is also known as viscosity breaking. To say it very simply, you basically break down higher molecular weight compounds into lower molecular weight compounds, which has low viscosity and low pour point. Now, the question comes here is, why do I need to make a compound that has low viscosity and low pour point? Why? I mean, what is the significance of this low viscosity and low pour point? Anyone who is able to figure out that? Why is this specific? These two words over here. Is there any need for that word, for them to be specific about this word low viscosity and low pour point? Anyone, while we talk about low viscosity and low pour point, why do we need to break it in such a way that they have low viscosity and low pour point? So try to think about this. I will not be telling the answer to this one in today's session. So these are the two questions that I'm giving it like a kind of, what do you say, you can have a look at it or think about it at a free time, in your free time. So why low viscosity and low pour point is emphasized? I mean, what would be the reason that you think for this? So so this vis breaking, depending upon the type of reactor that you have, it is classified as soaker vis breaking and coil vis breaking. So soaker vis breaking usually operates at a low temperature and high residence time. Coil breaking operates at a shorter residence time. So in this vis breaking process, you have totally two different types of conversions. So the first one is the minor conversion and second one is the major conversion. Then we come to the concept of delayed coking. So delayed coking is nothing but here you try to kind of do this coking process into two stages. You split them into two stages. One is primary, another primary mechanism or primary process, and another one is secondary process. In case of primary process, you break down the large molecules into smaller compounds, whereas in case of the secondary process, just a second. Active products of the primary process, sorry, this is not larger molecules, of the primary products are cracked to form some other compound, or we polymerize them to form some other compound. So this is about the delayed coking. So any questions so far? Or I think this should be enough for the concept review session. So if you have any doubts, you're welcome to let me know. Any questions? Or we can move towards the problem. So if you have any questions, then do let me know. If not, I think we can take as usual, we can take a short break for 5 minutes. So if you have any questions, you are welcome to let me know. Or please go through these questions and start solving them one by one, so that when we resume the session back, uh, start answering each one of them quickly. In case if you want to take a break, then please do return back within the next 5 minutes. For those who don't want, please solve through the problems that I have that is displayed for you. So we will resume it next 5 minutes. We will resume by 6:10, yeah, 6:11, not more than that. I hope we can resume back. So, shall we progress with the questions? So, what is the answer for the first question? Which of the following coal is used to produce high grade graphite electrodes for the application in electric arc steel? Is it sponge coke, short coke, needle coke, or none of the above? Which of the following coal is used to produce high-grade graphite electrodes for the application in electric arc steel? Sponge coke, short coke, needle coke, and none of the above. Yes, anyone? So it is, answer is needle coke. So kindly have a look at this, and then once you'll have a look at it, please let me know what is the application for each one of them as well. What, like, in case if for needle coke, one of the example where it is actually used is in the high grade graphite electrodes, then where this short coke and sponge coke is used, and what is typically the difference between sponge coke, short coke, and needle coke? The answer for this question is needle coke. But what is exactly the difference between all the three different varieties of coke, and what is the application for each one of them? Yes. Okay, try to find out, because this is there available in the course content, so you just need to have a look at that. Then once you do that, you will be able to find that their difference and then their application. So whenever you have, so these kind of questions, you need to actually know at least one application for each different types of code or probably the process, because you may expect these kind of question in your assignment or in the exam. So kindly have a look at them. So moving to the next question. So this question we discuss now, so I expect answers. Explain the effect of sulfur concentration in Doctor sweetening process. So I hope you remember what is Doctor sweetening process, and what is typically done, what kind of reagents we use. So in Doctor sweetening process, we use sodium plumbide. So over there we discussed about this particular concentration of the sulfur. If it is more, what will happen, and if it is less, what might happen. So now now I'm asking you to explain it in your words. So answers. I think this should be a easy one, right? So, in case of this doctor sweeping process, what will happen if you have excess of sulfur? So, excess of sulfur may create polysulfides, which will lead to copper foil corrosion, which will lead to failure of copper coil corrosion tests. So now tell me what happens if there is less of sulfur. In case of less of sulfur, then lead oxide will form, and because that sulfur compounds will react, the PBSR will react with the oxygen, leading to the formation of lead oxide. And once the lead oxide is formed, it may lead to failure in water tolerance test. So this is there. So please remember this. What will happen in case of the sulfur concentration is more or less in case of the doctor sweetening process. So you typically in case of this sweetening process you use sodium plumbite and sulfur Na2PbO2, and it's called sodium plumbite. So if there is excess of sulfur, it creates polysulfides and lead to copper foil corrosion test. And in case of if there is less of sulfur, then your PBSR may react with the oxygen, leading to formation of lead oxide, and that can lead to the failure in the water tolerance test. So please remember this. Just to please let me know in case if you have any doubts in the first and the second question, or else I think we can move towards the next one. So next question is, you see a process flow sheet. This is for delayed coking. Now you need to tell me what is this PNQ operations or the reactor system in this process flow diagram represents for. So this entire process flow diagram is for delayed coking. Now in this process, what component does PNQ indicate for? P and Q. You can actually look at the process flow diagram. If you look carefully at the process flow diagram, you may be able to kind of guess what does this component P and component Q may actually indicate for. See, component Q, if you see, after the stream leaves Q component, you actually obtain gas oil. So you have Q, this particular component or equipment. Once the stream leaves the component Q, you are going to get gas oil. So what could be Q? And then if you see in case of P also, that coke drum is actually connected to P, and from P you have this cooling tower which goes to reflux drum, and then you get the gas. So what you can actually kind of like assume, or what you can actually guess from this? No idea, no clues. Any idea on what does P and Q represents for? Anyone? So Q represents for, so since gas oil is going to come out, something is going to, it's a component which is actually going to separate the gas oil. So you can call that as either gas oil separator, or more specific word that you can give is gas oil stripper. So similarly, P, if you see, you are going to feed that component P with the feed, and then the product is actually going to go through a cooling tower and then into a reflux drum, and then the gas gets released, and the fraction of this reflux is actually feed again into the into the equipment P. So P is a fractionator. Q is a gas oil stripper and P is a fractionator. Any questions in this? Anyone? Okay, if you have no questions, then I think, shall I move forward? Okay, okay, so let me go forward. Um, hmm. So which of the following is the secondary conversion operation of crude oil processing? Is it cracking, misbreaking, coking, or hydroprocessing? Which of the following is the secondary conversion operation of crude oil processing? Any answers? So it is hydro processing. That is the secondary conversion process for crude oil. Secondary conversion operation for crude oil processing. So I hope there are no doubts. Again and again I am asking. In case if you have any, please let me know, or else it's fine. I mean, it's okay. So next question is, soaker is breaking process is high temperature, high residence time, high temperature, low residence time, low temperature and low residence time, low temperature and high residence time. Anyone? I think this also we discussed when I was talking about the concept of soaker whisk breaking process. So we talked about two types of visc breaking process. One is soaker visc breaking process and another one is coil visc breaking. So over there I discussed about the residence time. And over there I discussed also about the temperature. Anyone? So residence time is approximately in the order of 1200 to 1800 seconds. Now let me know. And for coil visc breaking it is in the order of 100 to 300, sorry, 300 seconds. So it's a low temperature, high residence time. So if you have any questions, let me know or we will move to the next one. Calculate the Watson characterization factor for N-propane. Specific gravity is given and TB is given. So this was a question that was left out from the last live interaction session. So I think since this is a numerical problem, please let me know what is the answer. What is the formula for correcting the Watson characterization factor? Formula. How to calculate the Watson characterization factor? I mean, what's the formula? Anyone? So I'll give out the formula. I think you can calculate it and let me know the answer. So Kw, that is the Watson characterization factor, is nothing but TB. Or just a second, I'll write it properly so that it will be easier. One by three, the entire this thing by specific gravity. So now calculate and let me know what's the Watson characterization factor value. Is anyone with the answer? Or I'll just give out the steps. So please find out the final answer. You need to add a factor of 460. I'm taking 1 by 3 as 0.33 divided by 0.8. So just calculate this value. So let me do that as well. Five, five, five. 10.25. So that would be approximately 10.27. Option C. So anything anything if you want to, any doubts if you have, you are welcome to let me know, or else we'll progress towards the next one. Any questions? Anyone? Okay, let's move on. Match the typical property of the crude oil with the difficulty in the conventional processing approach. So you have on the column 1, you have the properties of the crude oil. Now with these properties, what kind of difficulty will arise in the conventional processing approach? So you have 1, 2, 3. Need expensive hydrogen, refining problems, shipping problems. And you also need to tell me why this could be like leading to that problem. So, we need to know why certain properties leads to some problems. Just a second. Oh, Yeah, sorry. Due to this network problem, the call got disconnected. So let me share the screen. So this is the question. So the answers are P is 3, Q is 2, and R is 1. Sorry. So any questions, or shall we move forward for the next one? Let's just solve this problem. So the question is, vacuum residue have a condensation carbon ratio CCR of 15 weight percentage. API gravity is 8.5 degree API and sulfur content is 3 weight percent. It is fed into a delayed cooker at a rate of 4 lakh pound per hour. Determine the production of naphtha in percentage. How do you solve this problem? I think it's simple. It was discussed even in the tutorial part of the course. Vacuum residue have condensation carbon ratio 15 weight percentage. API gravity is given as 8.5. Sulfur content is 3, and it is fed into a delayed cooker at a rate of 4 lakh lb per hour. Calculate the production of naphtha in percentage. So I'll give out the formula. I think then it will be a bit easy. So naphtha will be equal to 11.29 plus 0.343 times CCR percentage. Remember, CCR here is in terms of percentage. So naphtha will be So if you do the calculation, 16.435. This is in terms of percentage. And if you want it to be, if you they ask you to calculate in terms of pound per hour, then you need to multiply this 16.435 divided by 100 in multiplied by 4 lakhs. So let's calculate that as well. Is 65740 lb per hour. So this will be the production of naphtha in percentage as well as in terms of pound per hour. So any questions in this? Like this, if you go and see in the tutorial problem, you have actually calculated the percentage of composition for gas, naphtha percentage, then you also calculated it for coke, gas oil, etc. And then you also calculated the percentage of sulfur in each of the following products. So this is just a very short version of that one. So any questions? I think we have. Okay. If you don't have any question, then solve this last one and then we can wind up for today. So this is something that is related to week 3. So here you need to find out the operations of P, Q and R. Again, see, check what is entering, what is leaving, and based on that I think you should be able to guess what could be the operations P, Q and R. So I think you should be able to get P and Q. R may be a little bit difficult. What is P and what is Q? You can see P, in case of P you have some atmospheric residues that is coming out, and in case of Q you can see vacuum residue that is coming out. And apart from that, in P if you see there are multiple components that are getting separated. Even in Q also you are getting multiple component separation, loop fractions. So it is some sort of a distillation column. What distillation we don't know, so let us write it as distillation. So if you see the products, one is the atmospheric residues, it is written. So P is atmospheric distillation and Q is vacuum distillation. And if you see R is some sort of a technique which you actually do it in the initial stage. So it's going to be a pre-processing or pre-treatment technique. So you have preheater already marked up. You have crude oil which is entering. So some sort of a technique which is going to help in this pre-processing technique. So the answer is desalter. So try to identify what kind of products are entering and what kind of products are leaving. Based on that, you will be able to kind of like come or make a guess on what could be the operation or equipment that is asked in the questions. So any questions from what we have discussed today? So we will conclude our session here. So in case if you have any doubts, you are welcome to let me know. Or in case if you have anything that you would like to discuss also, please related to what we have of what we have covered so far, then also please you're welcome to do so. Let me just stop sharing. Yeah, any questions, anyone? Okay, then if you so we have completed 4 weeks of live interaction session. So in case if you have any feedback for me regarding the way we conduct the live interaction session, also you are welcome to let me know. So currently we are I mean discussing, we have actually splitted the session into two halves. So in the first half for around 45 minutes we have a quick overview of what was discussed in the 2 to 2.5 hour content of lecture, and then later we actually move forward towards problem solving. So are you guys okay with this, or do you want more time for problems, less time for theory, or vice versa? Anything that you would like to give a feedback so that we can incorporate that from the next for the next 4 live interaction sessions that are pending for the month of August and September. Anyone, any feedback? Okay, so then I think I can conclude the session for today. So thank you all for joining today's live interaction session. I hope this session was useful. Our next live interaction session will be on 23rd of August, same 5 p.m. to 7 p.m. So I hope you are able to access these videos that are getting recorded, and also the presentation. So just in case for those who don't know, you can actually visit the course content page, the homepage for this particular course, Technologies for Clean and Renewable Energy Production, July, in this semester, the 2026 one. So if you go there on the left hand side, from where you access the week's content, at the bottom, you can actually see the problem solving session. So if you click on that link, you will be directed to an Excel sheet where you can find the YouTube video of this particular lecture or this particular live interaction session. And from there, you can also access the presentation folder. My email ID also will be given there. So you are welcome to email me regarding your doubts that you would like to clarify during the week. So I will try to respond to them as soon as possible. So I take this as an opportunity to thank Professor Prasenjit Mondal sir as well as the NPTEL team for providing me this opportunity to interact with you all on this Sunday afternoon. So till our next session, bye. Have a great weekend ahead, and keep working on the course. So thank you and have a great day. Thank you.